Okay, so we are going to wrap up our chapters on bonding. So we're at the end of the packet. I've kind of lost track of pages, I believe 22. We're just talking about hybridization. So if you have a hybrid of something, it's going to be a blend. That's what a hybrid means, in my opinion. I'm not sure what it means in bio. But what we're talking about is what is actually happening in terms of the orbitals. So we're going back to the S and P's and D's. No, not the D's, just the S and the P's. So when we're talking about the hybrid orbitals, we're thinking about those S orbitals, P orbitals, and where those electrons are in terms of the bonds, because remember the electrons are hanging out in the S and P's, so it's like they're sharing neighborhoods. That really doesn't make sense, but it's just kind of talking about how the orbitals overlap, that when we say there's a bond sharing, well, the electrons kind of have to now coexist in space. So which orbitals are they coexisting in? So let's look at what, this is all in your notes, and so just kind of explaining what is there. So if you look at I'm going to try to draw this. If we just looked at a carbon and the hydrogen. So look at carbon. It has, so right here, this is my carbon. No, excuse me, this would be the hydrogen. This is actually the 1s in a carbon. And then, let's not talk about the 1s, let's look at the valence. And then here's your 2p's. So that 2p2 is saying they're in these p orbitals. So if I have carbon in the middle, this is saying that I have an s available, and there are these S little circle ones, and then there are P available, which are, remember, my dumbbells. So they're saying that's where their 4 valence electrons are hanging out, because here's my valence electrons. Well, hydrogen is sitting over here. We have 4 hydrogens, and all hydrogen has is an s orbital. That's nothing very exciting, because that's all that hydrogen has. So at first, this is kind of what they thought just kind of happened, that the electrons just hung out, bonded, where they are actually in the orbitals. But what that would have done, an s orbital is different than a p orbital, so that would have caused something to be different in the bond angles. So what happened is, now that they were able to find the evidence, they realized that isn't the truth, and we know that an SCH4, remember we know this shape 4 is tetrahedral, and when they did the bond angles, a tetrahedral is 109.5. They were all equal. Since they were all equal, that meant this is not what happened. So something else must be happening. So, oh, there's my drawing. Okay, so what happens? This is a silly little thing, but think of it as they got blended together. So I'm going to so I need a total to make a 4 for tetrahedral then. I need 4 equal bonds. So where's that 4 equal bonds going to come from? Well, I'm going to take one of my s orbitals. I'm going to add it to 3 p's. So if I take one s and 3 p's, because remember that's how many p's you have, because if we draw lines, there is one s orbital, and there is, if I look at my 2p, because 1p doesn't exist, there's 3p orbitals. So that's what I'm blending together, and what it comes out is to 4 identical. So here's your 1s, here are your 3p's. What they have realized, these kind of form a mutant, a hybrid. Here's where the hybrid comes from, that they come out to 4 equal hybrid orbitals. That when they bond in those areas, that actually gives them a equal tetrahedral shape. So the name of the orbital is what you have to know. And the name of the orbital just comes from what was used to make it. So 1s and 3 p's. So we would say a tetrahedral orbital or tetrahedral molecule has an sp3 hybridization. Count the superscripts to know. If you need 4 bonds, this is, remember, the s is assumed, so 1 plus 3, this is what you use anytime you need 4 bonds. It will always be an sp3 hybridization. And so that's what makes it equal. Now that happens, it doesn't have to just be bonds. I can have ammonia, you still have to count where the electrons are going. So anytime the electron geometry is tetrahedral, that is when you get sp3 hybridization, because I still need a room for electrons. 1, 2, 3 electrons. So this electron geometry is still tetrahedral. The tetra, not tetrahedra, tetrahedral. So the shape, remember the shape is trigonal, pyramidal, but the hybridization is sp3 because you need to have 1, 2, 3, 4 areas for electrons. Anytime you need 4 areas of electrons, you have an sp3 hybridization. So this is now kind of showing what the bonding looks like. Here's the good thing, you don't have to draw these bonding orbitals because it would get really messy and that would be awful to grade. But this is what you're seeing. The carbon is what has the sp3 hybridization. Hydrogen doesn't have anything to hybrid with because all it's sitting over there is the 1s. So the red is recognizing the 1s and the purples are the sp3 hybridization that are all equal. Even if there's a lone pair, so this is showing you ammonia, even if there was 2 lone pair. Okay, so now let's look what's happening if I don't need 3 bonds, because here I only need 1, 2, 3 bonds on this carbon. And again, you talk about the hybridization around each element. And so around this carbon, it also needs 1, 2, 3. And the same thing, they found out that these are equal bonds around the carbon is what we're focusing on. So what has to happen to have 3 equal bonds? So if I only need a total of 3, they're only going to use 1 s, and they're going to use 2 of the p's because that's going to add up to 3 total orbitals. So 1 of the s and 2 of the p's are going to blend to make 3 total new orbitals. So we would call this an sp2 hybridization. You would use this whenever you have a trigonal planar electron geometry, e.g. electron geometry. And that is where we get the 120 bond angles. So again, 1s, 2 p's blended together, you get an sp2 trigonal planar electron geometry. So what happens? Here's the new vocab they're going to be talking about. Okay, whenever you have the hybrid, that's a sigma bond. Okay, a sigma bond, think of it like a primary bond. All bonds contain a sigma. So a single is always just a sigma bond. Well, let's think about this hybridization. So you had an sp2 hybridization, but how many total p's do we have? There's 3 of them. So these 2 form the hybrid. That means I have 1 p that was not hybrid. So this is where the double bond happens. So the double bond is going to be happening in a pi. So the pi is where the p is. So pi bonds then, pi bonds are your double and triple bonds. You get a sigma and a pi. So if we wanted to start drawing this, here is your sp2 hybridization. This is sp2. So there's your 1, 2, 3, 1, 2, 3. But it's like, wait a second, I still have a double bond. So if I could draw, there's my empty unhybrid normal p orbital. This, and again, 3-dimensionally, that is where the double bond is occurring. So the double bond is occurring in an empty p orbital, not empty, but an unhybridized p orbital. So what happens, and again, this is called the pi bond, and it's kind of a sideways overlap. This is why I think about what we talked about with our bond lengths. When you get a double, it's going to be shorter. You're sharing, there's more electrons being shared, it's a greater attraction. That's why it takes more energy to break the bonds. So this is my P. It looks a little bit prettier than mine. So this is your sigma bond, it's your primary bond that happens in the hybrid. The empty P's is where the pi happens. So a pi bond has to happen in a p orbital, not in the hybrid orbital. So this is again why we don't draw it. So this has an sp2 hybridization. So how do I know the hybridization? Count bonds, 1, 2, 3, or bonding areas. Anytime you see 3, you know this is an sp2 hybridization. Okay, what's going on here? So count, we have a 1, 2 areas that are actually being bonded. Both of them have only 2 areas. So this means then we only need a total of 2. You always use the S, and it's just how many P's. So an S and a P, so this is just an SP hybridization. Well, what is it left? There's 2 P's that were not hybridized. I don't know if that's correct word, but that's hybridized. So what does that mean? This is where Mahoney drawing this is again why we don't draw it. So here's one empty that's coming out. Okay, then yeah, there's another pi bond that's facing you in the face. Okay, can you see why we don't draw these? They would never, I've never ever seen them ask you to draw it, but they just might ask you to identify what hybridization is going on. Okay, so let's look at somebody that could draw it a little bit better. And again, this is what explains why the triple bonds have an even shorter. So this you can see it a little bit better. So the red, pink, okay, right here, this is your excuse me, hybridization. So the yellows, these are your empties. So the sp2 would be the sigma bond. That's my sigma bond. The yellows represent the pi bonds, which happens in an empty p orbital. So a triple bond is composed of 1 sigma and 2 pi bonds. Sigma happens in the hybrid, the 2 pi's happen in the empty p orbitals. Again, a triple bond has the greatest energy, takes most energy to break. They release the greatest energy, and they are also the shortest of the bond lengths. So this is, again, here you have your notes of what a definition. It's just the sigma bonds. The sigma bonds, they're your strongest, they're the primary. So everything has a sigma bond. And then you will start seeing the pi bonds when you start seeing multiple bonds. And that's where you get the overlap. It's using those, the P's not used in the hybrids. So a single bond, you know, is just 1 sigma. So a double has to be composed of 1 sigma and 1 pi, and so a triple bond is 1 sigma and 2 pi's. So we can count this. Let's just kind of figure out what we know about these. Let's kind of put it all together. This one I don't think was in your packet, so add it really quick. This would be antimony pentachloride. Now remember, this antimony can have an expanded octet. Carbon cannot have an expanded octet, but antimony can. So if I wanted to know the shape, okay, this molecular shape is, oh, and actually, okay, we're going to come to the hybridization on here. I know there's some of your notes that I skipped over. I'm going to tell you why. So first, let's just practice the shape. When it has 5, you know it's trigonal bipyramidal. Okay, 1, 2, 3, 4, 5 is just trigonal bipyramidal. The electron geometry and the molecular geometry is the same. Okay, hybridization, we are not going to talk about that for expanded octets. There's a little bit in your packet. Go ahead and cross it out because it is found out not to be true anymore. So it's not on the test. So you will only have sp3s, sp2s, and sps because that's the only one that has the evidence to support it. So this would never be a question on the hybridization. The shape you could, okay, polarity, look at all the atoms are the same. Remember, it's not drawn to scale, so this is a non-polar molecule. Even if it has a polar bond, so this can be a polar bond, but the molecule itself is non-polar. And this one, you're not going to have to worry about the bond angles either. Okay, nitrate. Actually, let's go back. I don't know if I have an empty one. Let's go ahead and do the nitrate. Let's count the electrons. So I have 5 plus 6 times 3 is 18. And remember, a negative means you have to add it. So that would be 6 plus 18, 24 electrons. If you tried drawing it like this, okay, so let's test. Oops, those are my dots. If you tried this 8, 16, 24, this is drawn with 26. This is how you knew that wasn't it. Don't forget the brackets and the charge. Okay, this has resonance. Remember, resonance is when you can draw the double bond. Now this one we can look and say what we know. Okay, look at the shape. 1, 2, 3. So this has a trigonal planar shape. It is around nitrogen. What is the hybridization? It's going to be sp2 because I need to have a total of 1, 2, 3 hybridization. Okay, let's count sigmas. Sigma, sigma, sigma. So there's 3 sigmas. And then pi is when you have a double, and there's 1 pi bond. Okay, bond angle, trigonal planar, 120 degrees. That's one you are expected to know. Now, polarity, this is an ion, so we don't talk about the polarity of an ion because it's a charged particle. So this wouldn't be a question as far as what is the polarity of this molecule because it's not just a molecule. It's a polyatomic ion. CHCl3. Okay, this one, looking at the math, I know carbon can't have an expanded octet, so that's why you never, ever, ever, can I say ever, put more than 4 around carbon. Never. It can't have an expanded octet. It's in the second period. Remember, anything in the second period, the 4 is max. So, 1, 2, 3, 4. This is an sp3 hybridization. It is tetrahedral shape. So its bond angle is 109.5 degrees. That is another one you're expected to know. And so then, what else was on there? Oh, polarity. So look at chlorine, 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 hydrogen. We've totally lost our symmetry. This is a polar molecule. So let's count 1, 2, 3, 4. There's 4 sigmas. Oh, back on that antimony, the antimony pentachloride, we forgot to count sigmas, and that one just had 5 sigmas. So you only get a pi bond when you start to get a double bond. Ooh, look at this guy. Okay, let's do this guy. Let's do HCN. And then I want you to add this one. 5, this has 10 electrons. So hydrogen, if you try to do this, I'd go 2, 4, 6, 8, 10, 12, right? 2, 4, 6, 8, 10, 12, 14. Now that's not going to work. Let's try a double bond. 2, 4, 6, 8, 10, 12. That's still too many. So it's going to end up with a triple bond. So 2, 4, 6, 8, 10 electrons. Okay, this is a linear shape, which means it's 180. It's a polar molecule because it's not symmetrical. There are 1, 2 sigma bonds, and then there are 1, 2 pi bonds because it's a triple bond. So this hybridization, 1, 2, is an sp hybridization. You would also say that nitrogen also has the sp hybridization because it's bonding and it has the lone pair electrons. Okay, draw this guy in. You may need to pause. Let's go to town here. Let's count these all up. So we couldn't look at the overall shape. We could just look at the shape at parts of it. So the shape around this guy, let's start there. This is 1, 2, 3. This is an sp2 hybridization, so it's a trigonal planar around this shape. What do we know about this one? Now, it's not drawn always to scale, so don't let them sucker you in. They're going to draw it, not necessarily draw it, because this only has 1, 2. I know it's drawn bent. It's not bent. This is an SP. This is linear. Same thing down here. This is an SP. I know that because there's 1, 2 areas of bonding. 1, 2 versus 1, 2, 3. So this is also sp2 hybridization. Nitrogen is also having sp. This carbon is having an sp because it's linear. This nitrogen is also having sp because lone pair take up space also. Okay, now see through my mess, let's count my sigmas. So 1, 2, 3, 4, 5, 6, 7, 8, 9. This has 9 sigma bonds. Okay, let's count pi's. 1, 2, because remember triple is 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's also 9 pi bonds in this. Okay, so that is the end of hybridization. There's some practice problems in the packet. And then if you saw, I want you to go ahead, please pick up the new packet and get reading on chapter 10, 11, which is we're going to start talking about intermolecular forces and some of the physical changes and what's happening between molecules, and review yourself on intermolecular forces. I'll put up the PowerPoint, or you can also look through the book to remind yourself of what's the difference between a London dispersion, dipoles, and hydrogen bonding. Have a great weekend, and we will see you later.